Anyway, thank you for the introduction. Good afternoon. I'm happy to be here to present our work. And this is about a novel data collection stack that we call Crystal. So, in fact, we hacked not only the Mac, but a little bit of everything. So, the stack is called Crystal, is based on synchronous transmissions, and if combined with data prediction techniques, it makes ultra-low power wireless sensor networks a reality. So, first of all, why did we need a new data collection stack? The motivation for this comes from our previous work, where we showed that by using data prediction techniques, we could reduce the amount of application packets sent over the network 100-fold. But, of course, this didn't translate into a similar improvement of the network lifetime. And the network lifetime is our goal as developers of the wireless sensor networks. In fact, we showed that the standard combination of CTP and box MAC with data prediction gave just 7 times improvement of lifetime. With our new Crystal stack, we didn't achieve 100 times improvement either, but we really got close to it, showing 80 times lifetime increase without compromising latency or reliability. So just a few words about how data prediction works. With data prediction, sensor nodes, instead of sending periodically their readings to the sink, compute a model that describes those readings. And later the sink can use this model and reconstruct the readings without even receiving them. When the model changes, the trends of the sensor readings change, something happens in the environment, and the old model does not represent the readings anymore. The nodes just send an update, a new parameters for a new model for the sink. In the result, the data traffic becomes really, really sparse, but also aperiodic and bursty due to temporal and spatial correlation of the sensor readings. But also the traffic becomes more critical because now every single packet carries more condensed information about longer periods of time. So having this in mind, we set 2 goals for our new data collection stack. First of all, it should minimize overhead in long periods of inactivity between those model updates. And second, when they appear, they should be delivered reliably and timely. Why current stacks do not achieve those goals? Well, they are wasting energy. When there is no data traffic, they are still maintaining the topology and they're doing idle listening. And when the traffic appears, they might be still too sleepy, and it might take a long time for the packet to travel across the asynchronously waking up nodes in the chain towards the sink. Crystal instead doesn't use any topology, it doesn't maintain one. It just uses glossy flooding under the hood. It makes all the nodes wake up in one accord once per reporting period that we also call an epoch. It makes nodes deliver quickly the data packets using glossy floods. And what is most important, it keeps the network awake just as long as needed for the pending updates to be delivered, adapting to the actual number of them in every single epoch. Before going into detail of the Crystal design, I will show you the peculiarities of the data traffic that it has to deal with. Well, we used 7 data sets coming from 4 real applications, covering months of real sensor readings with millions of samples. And one of those applications, denoted indoor here, is the widely used Intel data set with temperature, humidity, and light indoors. To save time, I will concentrate now only on 3 examples, 3 typical examples of those 7. Indoor light, soil temperature, and water chlorine. So they have different epoch durations, the reporting periods, starting from 30 seconds to 10 minutes. a different number of nodes. Without data prediction, every epoch, every node would report a sensor reading, resulting in as many of them as there are nodes in the network. After data prediction, this number of updates per epoch will be reduced significantly, but also will become unpredictable, unknown number. If you look at the distribution of this random number of data packets or updates per epoch, we'll notice that the data prediction does a job very well, quite often, in the majority of cases. Most of the epochs are empty. They are not carrying any data. And the first goal is exactly about this. Crystal should optimize for this case. There are some epochs with one update, and rest of the updates are grouped together with some other updates in other epochs. And actually, there can be many of them. 84% of updates in Interlight case come in bursts, meaning that they are together with some others in the same epoch. And Crystal should deliver them all within one reporting period. The third example, water chlorine, is quite different from the others, and it shows that those bursts can be quite large, reaching 40 updates per epoch. Well, Crystal uses Glossy, so I'll have to quickly introduce it now. Glossy is a network flooding and synchronization protocol, which is very fast, the fastest possible propagation by design, because the nodes forward immediately the packets they receive. And it's also very reliable. It avoids collisions, relying on constructive interference. It introduces redundancy, sending the same packet several times. Crystal is built of time slots, and inside every time slot it uses glossy floods for data and control traffic. So now I'm ready to start describing our protocol, and I will begin with a simplified case. I will do it step by step. I will begin with a simplified case where we at most had one update per epoch. And in this case, it would be enough just to make the network wake up synchronously at the same time once per epoch and have the originator of this update flooded using Glossy. This would work fine. The only thing missing is synchronization. We need the nodes to wake up simultaneously, and we need to maintain synchronization. For this, we use a separate slot, time slot, where we make the sync spread the time reference. Okay, but this would work fine in the simplified case, but it's not our general case. In general case, we are having multiple updates from multiple senders in every epoch. How could we deal with it? So what if we just make all those nodes, flood those packets, X and Y in this example, simultaneously, and hope that the sync will hear something? If you look at exactly the same situation with two senders, just an example, but from the network-wide perspective, they start their floods simultaneously, and after several steps, those floods reach the sync. And we show experimentally that actually sync receives one of them with probability 1, thanks to capture effect and redundancy of Glossy. Of course, it will not receive more than one, but even one is enough for our protocol. Now, if we go back to the timeline, we can answer this question. Yes, the sync will receive probably one of those floods. But what should we do with the rest? Remember, we need to deliver all the data packets within the same epoch. Well, the nodes whose packets was not delivered have to retry. But first, they need to know which packet went through, right? For this, we use a dedicated acknowledgement phase after the data transmission slot, where the sync just tells everybody, okay, I received packet Y in this case. Later, node 1, having received this acknowledgement for packet Y, knows that it needs to retry its packet. And node 2 knows that the packet went through, but still it needs to wake up to help others to forward their data. So they all wake up and replay exactly the same sequence of data transmission and acknowledgement slots. And they proceed scheduling those TA pairs one after another until suddenly they all wake up to forward somebody else's data, but there is no data remaining. So the sync receives nothing, and it tells this to everybody. Okay, I didn't hear anything. This pair of T and A slots we will call a silent TA pair. Well, in the ideal world, this would mean that the network could stop. All data was delivered, and they can go to sleep till the next epoch. However, in reality, collisions sometimes happen. Not very often, but still. So if we go back to our example with concurrent floods, and now the sync does not see anything here. It would reply with the empty acknowledgement, and if we were using the same termination rule as before, this would mean that the network would stop here, leaving some packets undelivered. To avoid this, we change our policy. We let the network proceed, scheduling more TA pairs to make other chances, to give other chances for the nodes to send their data, to have it delivered, to give chance for the network to recover from this collision. Now the packets X and Y get delivered, but when should we stop? Well, our modified strategy policy will be to stop after several consecutive empty slots and acknowledgements. In this case, 2, but in general, it's a parameter of crystal R. To summarize, every crystal epoch will consist of a synchronization slot, a variable number of data transmission and acknowledgement slots, depending on the number of packets in the network currently, and the fixed number of empty termination TA pairs. The question is, will this protocol meet our goals? Well, if you look only at the design, it should. If the epochs are long, and in our case they are, from 30 seconds to 10 minutes in our data sets, and the time slots are tiny, and they are in order of milliseconds, and even if we sum up several of them, we'll get tens or maybe a few hundreds of milliseconds, still much less than the epoch duration. Yes, it seems that the network is sleeping most of the time, and when updates appear, they get through quickly and reliably thanks to the properties of glossy. But of course, I have to prove this experimentally. And to do so, naturally, we could do it like this. We could take our application datasets and run test-bed experiments with all this data and measure directly the radio duty cycle and the reliability. But those data sets are worth months of data. This would mean years of testing. Of course, it's not feasible. And instead, we rely on some other approach. So we build an analytical model which is very precise to estimate the radio duty cycle based on the real application data sets. But we still run a lot of experiments. But we run them with shorter traffic profiles, lasting for hours. We do so, we measure the radio duty cycle, the short-term one, and reliability. Then we feed exactly the same synthetic traffic profiles to our model. We compute the estimate, and we show that the error that this model induces is just 1%. So the model is extremely accurate and can be used in this case to reliably estimate the radio duty cycle on real data. We ran all our tests in Interact testbed with various transmission powers on various channels at day and night, but now I will report only the highlighted parameters, the results for the highlighted parameters. The rest is in the paper. Before we could actually run the measurements with Crystal, and before we could use the model, we needed to tune some parameters of Crystal. And now I will proceed telling you how we did it, and I will fill this tiny, small, not that tiny, small table of the most important parameters that we needed. in the paper you can find more of them. And I will start from in-slot parameter, internal slot parameters, that are basically glossy parameters. They are n, first of all, the redundancy of the flood, the number of times glossy repeats the packet, and w, the maximum duration of the flood. They are interconnected. W limits both redundancy and the maximum flood diameter. And here we are having conflicting goals. First of all, we want better reliability, but for this we need more redundancy. And at the same time, we want better lifetime, and we need to reduce redundancy. So our strategy will be, for every slot type, select the minimum N and W that still provide good reliability and full network coverage. I will start from the S synchronization and A acknowledgement slots that are simpler in a sense because they are pure glossy floods with a single initiator inside. And now I need to select the appropriate redundancy N. We can see that from this chart that shows the average PDR of the flood as a function of the redundancy constant, that starting from 3, we are getting 4/9 reliability. If we go to 4 and more, we can get 5/9. But we would need to pay a price for this, because more redundancy means less lifetime. And in our case, 3 was enough, because Crystal also has other reliability mechanisms, and 3 was enough in achieving good reliability of the protocol as a whole. So we chose 3 for S slots and A slots. We needed to run a separate study for reliability of the T slot, because T slots are completely different. They are contention slots with multiple concurrent floods run simultaneously. And we needed to select appropriate N for all values of U, the number of concurrent updates. And the chart shows the probability that the sync receives one of those U updates as a function of N and the U, the number of them sent. And you can see here that, in fact, in those tests, sync always received an update. So the reliability was perfect. And you might think that we carefully chose this sync, a lucky node for which capture effect always works. In fact, no. We measured the same success rate metric for all the nodes in the network, and we can tell you that starting from N equal to 2, there are many of nodes enjoying the same perfect reliability, perfect success rate. Those lines suggest that starting from N equal to 2, the reliability is high enough, and it's not improving much further if we increase it to 3. So as before, in order not to pay extra, we chose N equal to 2 here. Okay. Now, when we have the redundancy determined, we can select the slot duration. The minimum, we need the minimum W that gives the full network coverage. And to do this, we measured the actual duration of the glossy floods as a function of N, and we just choose the corresponding value for the N's we chose for our slots, and chose W more or equal to the maximum of those measured durations of the glossy floods. That will guarantee the full coverage. Okay, I'm done with the slot-based parameters, but there are others. There are epoch level parameters to be measured and to be decided. First of all, to feed the model, we need to know how many slots we have in every epoch. We should have roughly as many of the data transmission slots as there are updates in an epoch. In reality, this number is a bit more because of retries, but this increase is negligible. You can see in the paper that it's really tiny. What is more important is the R, the parameter that tells how many there are empty TA pairs that signal the end of data transmission. And of course, the smaller R is, the less is the overhead. But with the minimum, the R equal to 1, the TA chain may stop prematurely before delivering all the data, as we saw in the example before. We measured actual probability for this to happen. And starting from R equal to 2, it's really small. It's 0.02%. So we could just go with it. But we wanted to optimize more. In some data sets, 90% of epochs are empty. And this is translated to those slot structures for R1 and R2. And you can see that the first choice would give us 2/5 savings in 90% of epochs. But it can risk reliability of the rest 10% of epochs that are non-empty and actually carry our precious data. So to assess the harm that the choice of R equal to 1 can impose, we ran stress tests with 40 concurrent updates in an epoch and R equal to 1. And here in this chart we report the actual stop position of the TA chain. You can see that in most of the cases it stopped after delivering those 40 updates immediately. Sometimes it stopped later due to duplicates, but this is fine. What is dangerous when the chain stops before delivering 40. But in fact, we can see here that it never stopped before 20, suggesting that it was really safe to use R equal to 1 in the beginning of this chain. And later it would be better to switch to 2 to get rid of those early terminations. In reality, we use a simplified rule that gives us the same savings. We stop if the very first T in the chain is empty, and later we use R equal to 2. So now we have all parameters we need for our model, and I can show it to you. And I will start with a simplified formula that gives the radio on time for an epoch containing U updates. And it takes into consideration only the slot durations. It sums them up and gives an upper bound, or the worst case, because in reality, those floods can take less time, and glossy stops after the flood is completed. So this more accurate formula takes into consideration the actual durations, the measured ones in testbed, and is much more accurate. I will demonstrate it here. To verify this model, to validate this model, we ran crystal tests with a synthetic traffic with fixed number of updates per epoch. And I will start with the first column of the results, showing the radio on time in milliseconds for the case with 0 updates. And it shows that the first model gives an over approximation of 13%, while the second refined model is very accurate. It's within 1%. The same is true for the traffic with 1 update per epoch and for all the others, showing that our model is accurate. And in fact, in this case, the reliability of Crystal was always 100%. So having this reliable model, we can use it to demonstrate that ultra-low power wireless sensor networks are a reality. So we use the original application datasets, we use the model to estimate the radio duty cycle of Crystal, and we report it here. And you can see that always it is below per milli or around per milli in one case, but sometimes it goes to stunning parts per million for datasets with really long epochs. And if we compare it to our baseline CTP without data prediction but tuned with tuned routing and MAC parameters, we can see that Crystal gives up to 78% up to 78 times improvement over the baseline. But we wanted to do more. It was based on the model, but we wanted to compare those protocols back to back. And we report here the results for 3 protocols: CTP without data prediction, CTP with data prediction, and Crystal. And we see that Crystal gives 70 times improvement of lifetime over the baseline without data prediction. And even if compared with CTP with data prediction, it gives remarkable order of magnitude improvement of duty cycle. To sum up, we started from showing that data prediction can reduce the amount of traffic significantly, but the current protocols do not leverage on it. They do not achieve significant savings. Crystal instead is a novel stack that we designed, takes advantage of the savings, of the reduction of traffic, and provides support for aperiodic data collection. And it achieves, together with data prediction, up to 80 times lifetime improvement over the mainstream stack of CTP and BoxMac. Thank you very much.
We have time for one quick question, and we are running out of time. Well, if there are no questions, let's thank the speaker again.